Well, hello and welcome again to our journey into number theory, into looking mainly at analytic number theory. And we've introduced quite a number of these very interesting and very beautiful arithmetic functions. All of them so far have been either multiplicative or in some cases completely multiplicative. And the risk of overburdening you, I'm going to introduce one more of these, which is the famous von Mangold function, capital lambda of n. And this one is very, very central to looking at the distribution of prime numbers and analytic number theory, but in some sense it's sort of a bit of an outlier in that it's an example of an arithmetic function which is not multiplicative, in fact. However, it's going to play an important role later on in the looking at the theory of the distribution of prime numbers, and we define it as follows. For each integer n bigger than 1, we define capital lambda of n, that's a capital Greek lambda, is you take, if n is a power of a prime and alpha is bigger or equal to 1, then you simply take the log of p and it's 0 otherwise. And we define lambda of 1 is 0. So it's an interesting function. If your number n is a prime power, then it just takes the log of that. So this is really picking out prime powers, and it's 0 otherwise, sends everything else to 0. So capital lambda of 12 is 0 because this contains a square, and so this is not a prime power, I should say. This is a product of two different primes, and or prime power times 3, and this one is 5 cubed, and so it is of the form p to the alpha, and so we just take log of 5. Now notice that L of 1 is not 1, and we know that if the function's multiplicative, then its value at 1 is 1, so this von Mangold function is not a multiplicative function. It's the first non-multiplicative function we've come to. Now, as usual, we'd like to know something about the sum over the divisors of this, and it turns out to be log of n. And so a little proof of that here. This is a little bit harder because we don't have, it's not multiplicative, so we have to be a bit more careful in evaluating this sum. So the result's true when n equals 1 because you just get 0 both sides. If n is bigger than 1, then you can prime factorise n in the usual way. And I'm going to take the log of n. So when you take the log of n, this is going to be able to turn the product of these primes into a sum, and you can use the log laws to bring the powers down the front. So it's just the sum I equals 1 to r alpha I log p sub I. On the other hand, we've worked out what the right hand side is, we're now going to have a look at the left hand side. So the only non-zero terms in this sum are going to come from factors of the form p sub k m, where m is 1 up to alpha k for each prime, and the k is going from 1 up to r, because of the way we wrote our n up here. So this sum of the von Mangold function over the divisors then is just a double sum. We want lambda of p sub k of m, and we let m run from 1 up to alpha k, k from 1 up to r. Now this we can evaluate. This is just log of pk, so that's easy. It's log of pk. Now this has got no m's in it. So if I put m as 1 up to alpha k, then this is just alpha k times that, and sum at k equals 1 to r, and that's exactly what we had before. That's what we showed the log of n was, and so we then have the desired result that this sum equals log n. Notice we can also apply Mobius inversion. Once you've got all these tools, you can play with them and see what interesting things come out. So I can apply Mobius inversion formula to that result we just had, and I can recover the formula then for lambda of n in terms of logarithms. So it's just the Dirichlet product of mu of d times log of the cofactor. And using the log laws, I can split this up into 2 bits. Now, this one here, I can take the log n out the front, and so I just have a sum of divisors of n mu of d. And we know that this is 0 unless n is 1, but when n is 1, log of 1 is 0, so that's going to vanish. And then I've just copied that one down, and so that just reduces down to there. So putting that together, we have that lambda of n can also be connected back with the Mobius function. It's minus sum over the divisors mu d log d for n bigger than 1. Full stop there. Well, there are a lot other things one can do, can play around and get other identities for these things. I want to move on to I'm going to call the derivatives of arithmetic functions. Do not confuse these with ordinary derivatives, but I'm going to use the dash notation for reasons that will become apparent. So if I have an arithmetic function, I'm going to define its derivative by this formula. To get the derivative of an arithmetic function, you just multiply it by log n. And that's the definition of this funny derivative. Perhaps I should put it in inverted commas here. It's not like the usual calculus derivative. The derivative of an arithmetic function, you just multiply it by log n. Now, I dashed of n is I of n times log of n, but then if this is 0 unless n is 1, and log of 1 is 0, so that's 0. And so, as you might expect, the derivative, in inverted commas, of the identity is 0. Surprisingly, the derivative of the unit function is just log n, because unit function is just 1, you multiply by log n. The identity that we had, that sigma sum over the divisors of lambda d is log n, which was our theorem 3.7, we can now write this as, I can put a 1 in here, and I can write this as lambda star u, and this is u dashed, so I can write lambda star u as u dashed. So we can get lots of interesting connections involving this new derivative. So to see that this definition has some point to it, well, we note the following result, theorem 3.8. If you take any arithmetic functions, then the derivative of the sum is the sum of the derivatives, which is easy to prove. Now this one should jump out at you. This is the product rule. If this was ordinary calculus, this is just a product rule, and the product rule still holds for this Dirichlet multiplication and for this new version of the derivative. That is, the derivative of the product is, you take the derivative of the first times the second plus the first times the derivative of the second. And we also have a little formula for the derivative of the inverse, which is slightly more complicated. It's minus f dash star f all inverse, provided f of 1 is not 0, because then the inverse doesn't exist in the first place. I'll leave A and C a little just exercises. For this one here, if you're going to do this, you might like to start from this, and you'll find that this comes out fairly easily then. Just to show you how it works for part B, to prove the really interesting one, that is the product, so-called product rule. Well, we start off with this product, and now we're going to interpret f star g, remember, is just the Dirichlet product of f and g, there it is there, and you take its derivative, you multiply by log n. And the trick now is to write n as d times n over d, and the point is I can then use the log laws to split this up. So this is now f of d times log of d times g n over d plus f of d times g of the cofactor and then log of n over d. I've just used the log laws on this term here. And finally then we just go back now and reinterpret this in terms of our Dirichlet product and derivatives, and this is the derivative now of f, and its Dirichlet product with g, and this is f and Dirichlet product with g dashed, that is g times log, and so it falls out very nicely. Now we can use this, we're not going to do much with this Selberg symmetry formula, but just to pop it in here that we can now use this to give a very simple proof of this very amazing and very mysterious formula called the Selberg formula. And Selberg and Erdős used this to give their so-called elementary proof of the prime number theorem, which was done independently by Selberg and Erdős. Elementary I use in a rather pointed way here. The proof is extremely complicated, but it doesn't use any analytical ideas. It just uses very, very clever number theoretic arguments to give a proof of the prime number theorem. And Selberg and Erdős did this independently, and the starting point for them was this remarkable formula here, which is known as the Selberg symmetry formula. And we might have a look at a bit of this later on in one of the later chapters. It connects together, it's the von Mangold function times log of n plus the sum over the divisors of the von Mangold function times the von Mangold function of the cofactor, and that sum is equal to the sum over the divisors of mu d times log n over d all squared. And we can actually get this really nicely just, again, using the power of the symbolism and this lovely Dirichlet product and derivative. Now, we've seen that lambda star u is u dashed, which we saw above. And so applying the product rule, we're going to get, we take the derivative of that times that, plus that times the derivative of that is the derivative of that. So that's u double dashed. Now we had a formula for u dashed above here, so I can plug that in, and I get lambda dashed u plus lambda star u is u double dashed. I'm going to multiply both sides by, I'm going to recall that mu is the inverse of u, and so I can plug that in and multiply, I can Dirichlet multiply both sides of this by u inverse. And that will then give me u times u inverse is the identity. Identity starred with lambda dashed is lambda dashed. The u inverse will get rid of this u, so I get lambda star u, and I get u double dashed star mu. And if I just translate this back into what we've got, lambda dashed is just lambda times log. Lambda star lambda is this expression. And then u double dashed, that means you're going to multiply by log twice, and so you take mu times this one evaluated at the cofactor, but you've got to do it twice because it's u double dashed. And so there's the result. Beautiful. Out comes the Selberg symmetry formula with just minimal amount of effort. Now, in the next few chapters, we're going to be looking in detail at functions defined by infinite series now. These are now infinite series of this form. That is, we're going to take f will generally be for us, well, here it's any function at all, but these will generally be arithmetic functions. And we're going to be looking at the sum, n equals 1 to infinity, of this fn over n to the s. And these series are a special kind of series. These are called Dirichlet series, and there's lots of books written about these. These have very, very important and interesting properties. And we'll be analysing these in some detail. So f of n is an arithmetic function. Such series are called Dirichlet series, provided it converges. Now, what can we do with these Dirichlet series? Well, one of the really fascinating things about this, and it really brings home the importance of Dirichlet multiplication, and it says the following. It says if you start off with two of these Dirichlet series, and let's suppose they converge absolutely for s bigger than some sigma naught, then we can multiply the two series together, fs times g of s, and we get another Dirichlet series h of n on n to the s, but, and here's the punchline, this h is just the Dirichlet product of these two arithmetic functions. Now that is a lovely result, and it really justifies the fact, if it needed any justification, as to why we defined this Dirichlet product in the first place. So the Dirichlet product enables us then to multiply two Dirichlet series together. And a little proof of that here, just manipulating the series. So provided we're beyond sigma 0, so we have absolute convergence, then the product of these two is just this. And I can pull the two series together like this. Now, what I'm going to do is, if you look at this series here, I'm going to put this n times m. I'm going to call this k, and I'm going to collect the terms. Because it converges absolutely, then we can rearrange the terms of the series. And so I'm going to collect the series for which mn is equal to k, where k goes from 1 to infinity. That is, this product is the sum k is 1 to infinity, and then I take a sum, m times n is k, fn g of m. And of course this in here is just going to be the Dirichlet product, well, I'm going to, of f and g, because I've got m times n as k. So this sum in here, once we fix k, this is a finite sum, and this is just going to be f star g of k, so I'll call that h of k over k to the s, and I've left, oh no, there it is there, over k to the s, and where h of k then is just this Dirichlet product of f and g. We can now prove the following corollary, which will be important in later work, and it gives us a lovely connection between the Riemann zeta function, which we haven't seen much of for a little while, and the von Mangold function. And this again is a very important and interesting result that we will come back and look at in a lot of detail in a much later chapter. So recall that zeta of s is this Riemann zeta function. It's 1 over n to the s, and it converges absolutely for s bigger than 1 and uniformly. So since this series converges, well, it converges uniformly by the Weierstrass-M test, which I'll leave you to check. We can therefore, once we know it converges uniformly, we can differentiate both sides of this, and we obtain this here. You might like to just check, if you take the derivative of 1 over n to the s with respect to s, then this turns out to be minus log n on n to the s, which I'll mention again in a moment. And the corollary to this is that minus zeta dashed over zeta has, look what it has as its Dirichlet series, it's got the von Mangold function up in the numerator. So this is the Dirichlet series corresponding to the von Mangold function, and this turns out to be none other than minus zeta dashed on zeta. And when we start looking at the proof of the prime number theorem, this is going to be very important for us. By the way, notice that this here, forget the minus for the moment, this is the logarithmic derivative of zeta, just to observe in passing. Okay, the proof of this, well, the proof goes like this. I'm going to prove this corollary, so I start off by letting f of s be equal to this Dirichlet series for the von Mangold function, and I'm going to put g of s to be zeta of s, so that's 1 over n to the s. Now this 1 here, of course, is just our unit function, so I can write this now. I can write the product of these two. When you multiply the Dirichlet series together, then that's the Dirichlet series of the Dirichlet product of lambda and u. Dirichlet product of lambda and u, but we saw before that that's equal to u dashed. When we take the Dirichlet product of these two is just u dashed, and to take the Dirichlet derivative you just multiply by log n, so this is 1 times log n is log n, and this of course is, as I said, just minus zeta dashed. just to convince yourself there, if you want the derivative of n to the s, then that's the derivative of e to the s log n, and that's just log n times e to the, sorry, I really meant a minus in here. So this is just minus there, and this is minus here. So when you differentiate this, by definition, this is e to the minus s log n. And when you differentiate this with respect to s, you just bring the log n down the front. You've got a minus there, and then you get back to where you start from, which is 1 over n to the s. And that tells me then that the derivative of zeta is just this thing. And so there is our lovely relationship, and as I mentioned, this without the minus here, this is just the logarithmic derivative of the zeta function. Now, of course, some of you may be aware of the Riemann hypothesis, which is to do with the zeros of this function, and you see that this will not make sense if this term here happens to be 0. And so that's what we'll see a bit later on when we start looking at the proof of the prime number theorem and how it connects in with this famous Riemann hypothesis.